Researchers have gained new insights into how bacteria move in complex environments. Bacteria move using a system called swim and tumble. They swim in a straight line for a bit, then tumble in a circle, which gives them a chance to correct their course. They can't see where they're going. They can't see at all, but they can sense and follow gradients of increasing concentration of food, like following a delicious smell into the kitchen. This type of movement is called chemotaxis, with the chemical that's attracting them being called a chemoattractant. Chemotaxis has been well studied in bacteria moving in a clear area, but in the real world, such as inside the human body, bacteria often have to get past a lot of obstacles. So, how do obstacles affect bacterial movement? I'm Ruby Osborne, and I spoke to Dr. Sabrina Rashid from Carnegie Mellon University about how bacteria fare in special obstacle courses built into tiny chambers.
The way the experiments were set up, like there were tiny chambers with different obstacle coverage. For example, in one chamber, there is absolutely no obstacle. So the area that the obstacles occupy is 0% of the total area of the chamber. Then we gradually increase up to 64% obstacle coverage. In each of the chambers, we introduce the chemoattractant media, and then we introduce the bacterial cells from the opposite side through an inlet. Then we record how long it took for the bacteria cells to reach the source of the chemoattractant and eventually escape the chamber. Despite how much we increase the obstacle coverage, the time it takes for the bacterial cells to escape from the chamber is roughly the same. So we hypothesize that probably in the presence of the obstacles, there is some kind of feedback mechanism that allows the bacterial cells to adapt their movement so that they can compensate the longer path of the higher obstacle coverage. And then we update our computational model to see that adding a component of adaptive tumbling following a collision with an obstacle can explain this kind of behavior or not. And we do see that incorporating an adaptive tumbling mechanism following a collision actually explains this behavior.
So, when you say an adaptive tumbling mechanism, what does that actually mean? What are these bacteria doing differently when there's obstacles there?
The bacterial cells are moving in a combination of swimming and tumbling. So we are measuring how frequently the bacterial cells tumble. When there is no obstacle, like the chamber is absolutely free, and they are free to move in any direction possible, they do tumbling very frequently. But when there is an obstacle, they do these tumbles less frequently. So if when they're moving in the right direction, they can continue that run for a much longer period of time. So that allows the cells to more or less compensate for the higher obstacle coverage, allowing them to more or less take the same time to reach the desired food source or the desired location.
Why is it so important that we know how bacteria move? How is this actually going to help us?
This actually gives us an idea about how this kind of unicellular organism might be navigating complex terrains. We get possible insight based on that how other cells like cancer cells or even bacteria cells as well, how they're spreading in a system. In case of antibiotic resistance, maybe if we want to take a physical approach to how to stop spreading harmful bacterial cells, and if we can model that accurately as we show here, then if we are trying to fight that cell spread, then we can probably come up with a better informed mechanism to how to do that.
How similar is the movement of cancer cells to bacterial cells?
This is at this point like purely speculative. Whether they move in the same fashion or not, depending on their exact physical criteria of different cells, we might have to tweak how this physical environment is actually affecting their actual movement. But overall, the idea that there might be some kind of feedback from the physical environment, that insight might be helpful.
And you said that as well as the biological applications, there's also a more technological use for this model. Could you tell me a bit more about that?
We know bacterial cells, like a group of bacterial cells, they're sensing some chemical or sensing some concentration and then moving towards. And actually, we do this kind of task in computational system as well. For example, in swarm robotics, where different robots are actually communicating and coordinating it with each other to find a common goal. If it's in a search or rescue mission, they have to say, for example, find a source of fire or find some victim trapped in things. in that way, the way the swarm robotics is working, it's similar to way the bacteria is actually finding its food source or chemoattractant. And oftentimes, if we're doing this kind of search and rescue mission, there will be many, many obstacles that the robots have to encounter before reaching the common goal. We actually show in simulation that adopting this adaptive tumbling mechanism from physical environment actually shortens the search time for these swarm robots. So that way we can show that it has a potential application in this kind of computational problem as well. We show that in simulation only, but in future it might be a good experiment to try that in real life systems as well.
That was Dr. Sabrina Rashid from Carnegie Mellon University, and that study was published in the journal PNAS.